So if you've been watching all of my videos, you've gone through a whole bunch of videos talking about generics, associated types, why use protocols, when not to use generics, and so on. And in this video, we're going to be talking all about generics and the compiler. And I want to just tell you why we're going to talk about this topic first of all, and where is it leading? Well, it's leading to the likes of opaque and box protocol types. Now, in order for us to skip over to this, we really need to understand how the compiler and the generics are going to work together. And we're not going to dig like super deep into this. We're just going to look at it at a high level and for us to understand, okay, what's the compiler thinking and when are we going to get these warnings? When are we going to get these messages? And how do we fix them? And how do we write code prior to the compiler even looking at it, knowing that it's going to work properly? So with that said, let's just jump straight in because it's not that difficult. You've just got to think like the compiler, all right? So let's just do two examples here. We have let num 1, and we are now the compiler. On the right hand side, so first of all, we have a let, so we know we're a constant. Now, followed by that, we have a variable name, okay, that passes all of the tests here that it's a variable name. We're happy with that, and it hasn't been declared before. We're happy with that. To the right of that, we don't have any type annotation here, so we're going to have to work it out. We have an assignment operator, an equal sign, and to the right of that, we have number 1. All right, we don't have 1.0, we have number 1. We don't have the 1 with inside quotation marks. We don't have anything else. We just have literally the symbol or the character number 1. So as far as we're concerned, we know that this is an integer, all right? And because it's going to be nothing else. Now, if we had 1.0, we would assume, well, we would infer that it's a double, okay? And when we use the actual type annotation here, we see then it is a double. And when we come back again and we see that it's an integer, all right? So, and with the same thing with the string, right? We see here with quotation marks to the right of it, we see DAVID, it's a collection of characters. And when we look at it, we see that it's a string. No surprise there. So do we need to say that it's a string? No. Can we say that with type annotation that it's a string? Yes. But the compiler has already inferred to the right of it, this can only be a string. So when we change the name to a var and we say name is equal to Thorn here, we see everything's perfectly fine because we've told it what type it is, and all we're doing is we're just changing the value of it because it can be changed. So the compiler is perfectly happy with this, all right? However, if we now change the value of name to 1, it doesn't like it because obviously a variable has its type as it was declared, right? And we can't change that. We can change the value of that one variable, but we cannot change its initial type. So it doesn't allow this. Okay, so this is us already thinking like a compiler. So when we have a function and we say add, and we say a is then int, and then b is then int, and we return a double, you know, this is going to be a little bit more difficult because we're not going to be able to say here a and b because cannot convert return expression of int to return type double, you know. But this is like, hey, wait a minute, when this is 1 plus 1, then this should just be 2. You know, the compiler isn't there to do your mathematics for you. It's just a compiler. It's not supposed to do this, right? It's supposed to follow the rules, the strict rules that are there. But you can let the compiler do the work for you as well. This is the whole idea. The compiler isn't lazy. The compiler is like, hey, here's my rules, and if I can guess what you're doing and it's correct, I'll do it for you, right? But if I can't guess, I'm going to warn you about it. So this is how you and the compiler need to work. Now, then when we come into generics, so we've got this our add function, which this is explicit. It's only an add function for integers. We take 2 integers and we return an integer. Okay, super fair enough. So now we want to then add doubles. We've talked about this in another video. So we could come here and say double, and we've also done generics as well. So we could then just say add, and then we could say then double here. This would be absolutely pointless because we are literally just writing the same function here and just doing u and returning u. This is not generics, even though this double is not a protocol, right? It needs to be a protocol, and so you can't constrain it with a concrete type. So here we can say additive arithmetic here that we now get this add function where we can add basically any struct, any type that adheres to the additive arithmetic. Okay, so we've seen this already, but how when we come to use this, and we say 1.0, we say 1.0 and 3.0. How is it that it's worked out what result is, right? And what function has it used? Well, you can see here that if we comment out this, you can see that it doesn't have an alternative for this, right? Now, if we uncomment out this and we comment out this function and we run this, and we can then come and say result 1 here and do 1, 4, and then 1.0 and 4.0. We can see here that we're getting exactly the same function. We've done this before, so this is what you've got to think. You've got to think like the compiler as well when using generics. Is can the compiler work out, can it infer what these two properties are? Okay, so now here is the question, is when the compiler sees a usage, you have to remember that the compiler's job is to convert this code that we've written in Swift and through multiple stages give instructions that a CPU or a GPU can process. All right, and there's lots of stages between that, and we're not going to get into it, but the ultimate aim is to take this code here and convert it to a way that the computer can actually use that code as computer code, right? As in machine language, right? And so when it sees this, it's going to convert this one line here to something that it knows how to convert. And it's not caring about generics right here. It's just looking at it and saying, I have an add, and I'm adding here two integers, and that's what it's going to convert it to, right? In the future, in the background, it's going to convert it to 1 plus 4, right? And then they're going to do different operations in the CPU, this, that, and the other. That's not what we're talking about, but that's what it's going to be. And this one is going to say, then we are adding 4.0 here. It's not going to say it's going to be the add generic function of this, that, and the other. This is what it's going to end up being somewhere later down the line, right? So we've got to think like this. Now the question is when let's just get rid of all this, right? And when we want to when we want to make a struct here, and we've got like an action, and we have then the t, excuse me, the t, and then we have a value. This is then going to be t, and it's going to be t, and then we're going to say get value, and this is then going to be t, and we say then value. And we don't necessarily need an initializer, sorry. We can say here action, and when we come to instantiate the action here, and we say 2, the compiler's already worked it out, right? Because it said, well, wait a minute, if I'm initialized with a value here, I can look at what type this one value is, and that will then tell me what this is going to be, and this t is going to tell me what this is going to be. So we didn't actually need to have any generics here. We could just literally use it, right? And when we look at the action, we can see it's action of type integer. So the compiler has already known this action is only for an integer, and so it knows it at compile time, right? Now the difference is that if you've got something at runtime and at compile time, so you want for the most efficient code to run on the mobile device or on the application or whatever it is, or on the server, you want it to already be optimized by the compiler as much as possible to run as fast as possible with the least amount of instructions required to be able to process that one command. So you want everything to always as most efficiently run at compile time. Now, however, if you're compiling your code 100 times a day, which can happen, then you also want that the compiler is as fast as possible. And so you want to give it as much information as possible. And if there is a difficult thing that it needs to work out, then if there's a difficult thing it needs to work out, then you're going to have to give it a little bit of a help, because if every single time it has to infer these things itself, it has to guess these things itself, then this is going to take more instructions during the compile time as well. So generics and the compiler, at the end of the day, you're using generics to write less code but use it everywhere. And the compiler is there to convert these generics into machine code that can be used as instructions from the compiler. However, you don't want to make the compiler to do all of the work. You want to let the compiler be as efficient as possible, but you also need to be as efficient in your coding to tell the compiler what each thing is going to be. So let's now talk about, let's remove this. Let's make a protocol called tester1, right? Or just like tester. And this is going to have an associated type of T, and it's going to say get item, and this is going to be of type T. All right, very, very simple. So let's make the struct now, and we'll say tester one is going to implement tester one, and then we can say the gets. We can say the gets item, and we're going to say the item here, and we're going to return item. And up the top here, we're just going to say here t is equal to int, and we will then add a item here is then of type t, and we'll initialize it with this. All right, we inheritance from. Oh, my mistake. Yes, stupid. There we go. So, oh no, we wanted t here. Sorry, my mistake. So now we have a generic struct. So let's create our struct now. This is not much different to than our action, right? But let's just say item and tester1 here, and now we have the tester1 t. So let's just try using 1 here, and you can see here that the compiler is perfectly fine about it, and it inferred that the item t is 1. All right, but when it gets down to more difficult situations, when we start making a second type of tester, all right, and we can come here and we can copy this and say item 2, for example, and item 1. Let's just do this. This is fine. There's no problem with this. These are both two tester protocols. So now when we come say get tester, and we're going to say value here, and we're going to say then integer, and we'll say tester, all right? And now we'll return this, and we'll return a tester and value. Let's have a look what goes on here now. You see, we're starting to cause these problems because this tester is a protocol, right? And we're saying we're going to return a protocol, but because this protocol has associated types, it's not possible for the compiler to know what concrete type this one function is going to return. And this is where the problem occurs, and which is why you've got to start understanding what is happening here. So we can't even get to this line 52 here because it doesn't know how to work this one out. And this is where the any tester comes into play. And this is where you've got opaque and also boxed protocol types. So an opaque protocol type is one where the compiler can work it out at compilation time, right? It knows the exact concrete type that it's using for this one protocol. Okay, and right here we are saying that we are returning a value, right? But we're not saying of what concrete type we're using because we're just returning a concrete type. And this is where the any comes into it. And when we do this any, and we look here at this tester, we're getting any tester. And this is where you're starting to come to runtime now, because we could say if value is equal to, well, let's just use a switch statement because it could be multiple things, and we'll say case 1, then we'll return tester1, case 2 will return tester2, and default we will return, let's just say, another one, just for the sake of saying tester default here, all right, just to be exhaustive from it, and we'll say value here, all right. So now when we say the different values, we can start printing these out, tester1, tester2, tester3, and we come and start printing these out, tester3 here, and we run this, and you can see here we get type tester1, type tester2, and type tester default. So you can see that all of this code in here has happened at runtime because it doesn't know what the value is at compile time. So this is where the generics and the compiler they start like conflicting with each other. So you need to write code. Your goal is to write the most efficient, fastest, cleanest, and smallest amount of code possible to be able to deploy it and run on your system, right, as best as it can. And so your always aim is to be able to have the compiler work as quick as possible to get as much code written in the shortest amount of time. But you want to try and avoid any bugs. But usability, it can be that here you just don't care about the implementation. You just like, I just want a tester. That is it. But you've got to balance out here now whether you want the compiler to do the work for you, or whether you want the runtime to do the work for you. And this is why it's really important to understand when the compiler is working for you. Now, obviously, the compiler has compiled this code, but this get tester code, but there's a lot more that it's got to do. There's a lot more business logic it's got to do in here. Because if it does get 1 or 2 or 3, you could simply just convert this to 3 different functions, right? You could convert it to get tester1, get tester2, and get tester default. This would be far more optimizable for the compile time, because this has got to happen at runtime because you've got any. And if you said get tester1, and then said here tester, right? And you always returned tester1, and we did the value, and now we say tester, and we say get tester1. Now let's have a look at what we've got. We've still got any here, but well, it's when we've got tester1 here, you've still got tester1, right? But you've not explicitly said that you're using a protocol. So when you start removing this, when you start removing the implementation for it, this is when you start having to use the compiler. But this is where we start jumping into the realms of opaque and also box protocol types, where we start having to declare what is inside of our type. And the whole point of opaque and box protocol types is hiding the types used for this one. For this one type alias, for this one associated type, we're trying to hide it. So this is where it's important that you understand how the generics and the compiler works. And now you don't necessarily, it's good to get these warnings, and it's good to be able to change it around to see, okay, how can I get a tester here? But when you see this any, you need to work out, okay, what is happening behind this one any, and how is the compiler helping us here? Is it helping me here, or is it making it more worse is it making it slower in the runtime? All right, is it making it slower in the compile time but faster in the runtime? Well, I'd prefer to have it slower in the compile time and faster in the runtime, always, every single time. So with that said, I hope that this gives you a better understanding now of how the compiler and the generics. You should always be writing code. You should always be writing code with the compiler checking every single thing that you've written. All right, and your compiler is your best friend, especially with Xcode. It's so fantastic. It literally will give you code completion. It will tell you what's right, what's wrong, unused variables, this, that, and the other. It's always going to tell you where you make a mistake, and sometimes it's going to tell you where you've got memory leaks and all sorts of stuff. So the compiler is your best friend, and writing generics in the right place at the right time is also your best friend. Okay, with that said, this is a nice segue onto the next video, or a video in the future is going to definitely be opaque types and also box protocol types. But I thought this video might just give you a little bit of an extra insight to how your mindset needs to be for these one things. And then if I decide later on that I didn't cover everything in this, or I didn't give enough introduction to it, I might make another one. So it could be that tomorrow's video is another one about like this as well. With that said, don't forget to like, subscribe, share, and do all of the other social media things that you can do to it. I hope you've got something out of this video. I hope you've learned something from this one video, and I hope it makes you a better, more informed Swift programmer. I only do these videos for you. I don't do them for me. I want to pass my knowledge on, and I hopefully want to make at least one or more competent, successful Swift programmers for the world to use, because we need more competent developers. With that said, thank you very much for watching. If you've got any comments, feedback, concerns, questions, etc., then as always, let's start a conversation in the comment section down below. Thank you very much. See you in the next video. Ciao, ciao, and goodbye.